Hello everybody, in this video we are going to talk about something called entropy, which is denoted by the uppercase letter S. Entropy is the measure of the number of arrangements, or as scientists like to call it, microstates, that atoms in a system can attain. In other words, entropy is a measure of the uncertainty, chaos, or randomness of a system. Since a system becomes less predictable, or more random, or more chaotic, or more uncertain, when there are more possible arrangements, or microstates, that atoms can take. So the more microstates, the more random it is. And we can take an example to see this. So in how many ways can we arrange two atoms labeled 1 and 2? Well, you can reverse the order and you would get that. And there are only two possible ways to arrange these two atoms. Now what about 3 atoms? 1, 2, 3. Well, there are actually more ways to arrange these atoms, so we could do 1 and switch these two to get 3 and 2, and we could start with 2, and we go 1, 3. We could start with 2 again, but we could go 3, 1 this time, and last but not least, we can start with 3, and we can go one of two ways. We can go 1, 2, or 2 and 1. So there are a total of 6 ways to arrange these 3 atoms, as opposed to 2 ways to arrange 2 atoms. So, in other words, this system with 3 atoms actually has a higher entropy, while the system with 2 atoms actually has a lower entropy, since there are less microstates and it is more predictable. Because if you think about it, I could just take a guess and guess this, and 50% of the time I would get the orientation right, because there are only 2 possible orientations that 2 atoms can take. Now, for 3 atoms, there are 6 different possible orientations that these atoms can take, and if I choose a random one, I would have a 1/6 chance of getting it right. So it's obviously less predictable, since it's harder to predict which microstate exactly it will be, because there are 6 possible microstates that these 3 atoms can take. Meanwhile, it's a lot easier to predict what 2 atoms can take. And obviously, if you have only 1 atom, well, there's only 1 microstate, so you have a 100% chance of guessing the microstate since there's only 1. So this leads to a very important part about entropy. As we just said, there are more possible ways to arrange 3 atoms than 2 atoms. Therefore, it is harder for us to predict the arrangement or microstate of 3 atoms than it is for 2 atoms at any one moment. Or, in other words, 3 atoms can be more random than 2 atoms. Therefore, 3 atoms have a higher entropy than 2 atoms. And that's basically the summary of what I just said. Now, this is really oversimplified, but oversimplification allows us to understand things, and that's what we're going for. So this actually leads to a very important point. The more of a substance there is, the higher the entropy. So, since we have more substance here than here, this has a higher entropy. Now, there are many other factors. The second factor I want to talk about is temperature. How does temperature affect the entropy of substances? So, let's just say T1 is at 0 Kelvin. Let's just say T2 is at 100 Kelvin. And let's just say we have a sample of gases. So let's make our gas neon, actually. Now, at 0 Kelvin, don't you agree that the average kinetic energy, aka temperature, of the particles are super low? And if they're super low, doesn't that mean that they're not going to move at all? Well, they will move, but just very, very slowly. So, in this case, when we have such a low temperature like 0 Kelvin, these particles are essentially not moving at all. And as we will later learn, at 0 Kelvin, you have essentially no average kinetic energy, which means that theoretically nothing should be moving. But in our case, let's just say that these neon particles don't have that much motion. And if they don't have that much motion, they can't really arrange into many microstates or configurations since they're kind of stuck in one state since they don't really move at all. So they're kind of stuck, right? Now, what if we increase the temperature to 100 Kelvin? Well, the neon molecules will obviously move around more often and thus be able to have more microstates and more possibilities of, arranging themselves. Like this could go here, this could go here. While in this picture, these atoms are kind of stuck in place because of such a low temperature. So what I wanted to emphasize was that the higher the temperature, the more random atoms can behave because they can adapt to more microstates at higher temperatures since they have more energy to do so. It's like if you don't eat something for a long time, you will be tired and you won't have that much energy, so you won't move around a lot. There's not a lot of chaos going on. But once you have that spark of energy, guess what? You can move around a lot, and that causes chaos, which, if we remember, has to do with entropy. Higher chaos, higher entropy. So that's a very important part. And thus, we conclude the higher the temperature, the higher the entropy. Now, this is assuming that the particles are the same because we want to keep everything constant and only change the temperature in this case. Now, let's talk about the entropy of the states of matter. Now, you might understand this, and let's just go over it. So, gases are free-floating particles that can move apart from each other, like in this image. So, obviously, there's a lot of randomness that can go on there. Now, liquids are particles that can move past each other, but cannot move apart from each other due to intermolecular forces. So we'll call liquids medium randomness because they can still move around, but they are locked close to each other because of the intermolecular forces. While for gases, well, they can essentially do whatever they want. So we can see the hierarchy of randomness, and not last, but second to last are solids. Solids are particles that are practically locked in place, and of course there are exceptions, but we kind of consider solids as just essentially locked in place. Not exactly, because we have amorphous solids, which we know are malleable, so they're locked in place for the most part. And these particles have very few microstates, low randomness. And that's because let's take a crystalline solid. We know crystalline solids have atoms arranged in a certain way, and it won't budge. So there's not many microstates that I can take. Like this atom can move, maybe 1 centimeter that way or 1 centimeter that way. Well, a centimeter is actually too big. Maybe a nanometer or maybe even a picometer to the left or right, but it doesn't have that much freedom. Now let's talk about aqueous solutions. This is where things get a little bit tricky. Aqueous solutions have both liquid particles and solute particles. So since there are more substances, as we mentioned before, the randomness of aqueous solutions is generally, but not always, higher than that of liquids. So it is generally, but not always, higher than that of liquids. So it has a medium-high randomness, let's just say. So therefore, we can conclude that the entropy of solids is the lowest, and the second lowest is the medium ones, so that's the entropy of liquids, and then comes the entropy of aqueous solutions, and then comes the entropy of gases. Now, let's actually give a general value for entropy as well. So let's just give numeric values, and let's make this really arbitrary. Let's just say solids is 1, liquids are 10, aqueous is 15, and gases are 100. So this is a general rule of thumb. It's very vague and doesn't always work, but generally, this trend can be numerically represented by numbers that differ in large magnitudes to show that, of course, the entropy of gases is so much higher than the entropy of solids. So remember that this is a general trend. It doesn't always hold true. And generally, when you do this, you want to make sure that you are able to quantify things. And I'll talk about that a little later. So let's talk about one last thing. For a state of matter, substances with a higher molar mass typically have a higher entropy. And this is due to the number of ways electron clouds can rearrange themselves. And note that this is at a constant state of matter, so we would be comparing a solid versus a solid, a liquid versus a liquid, and you get the point. And this is because higher molar mass, as we know, equals more electrons, and that equals more ways to arrange electrons since there are more of them, and this leads to higher entropy. And this goes back to the point that the more stuff you have, the more entropy you have, as we mentioned right at the beginning with the atoms. So let's scroll back down and let's continue talking. So use this rule about molar masses as a last resort, as you will see for an example problem that we are about to do. So these are the factors that determine the entropy of substances. And of course, there are more, but these are the basic ones that we should know. Let's do some practice. I want you to pick the one with a higher entropy. So pause the video, and once you're done, we can start up and begin. All right, I'm going to assume that you're done. So let's choose the one with a higher entropy. 1 mole of helium versus 1 mole of argon at the same conditions. So we're keeping everything constant. The only thing we're changing is the atom in question. So how do we differentiate between these two? Well, they're at the same temperature, there's the same amount of stuff, so we can't use the fact that more substance equals higher entropy or higher temperature equals higher entropy. We can't use those, but we can use this rule, this last resort rule, that higher molar mass equals higher entropy. So in this case, 1 mole of argon will actually have a higher entropy than 1 mole of, let's see, helium gas. So look at that. We solved the first question, and let's just circle our answer. So argon will have, of course, the higher entropy in this case. Now we have two identical cups of water, cups A and B, but cup A is 100 degrees Celsius and cup B is negative 202 degrees Celsius. So everything is kept constant except for the temperature. Well, guess what? Higher temperature equals higher entropy. So guess what? Cup A will have the higher entropy. And the determining factor is temperature. And let's write the determining factor for this. It's actually molar mass. So let's do water vapor and ice. So I'm not giving you the quantity of substances, so you should just assume that it's the same quantity. But what's the difference? Well, water vapor is a gas. It's actually water in the gaseous form, and ice is just the solid form of water. So guess what we said? We can assign values and say that water vapor will have 100, and ice will be 1. And guess what? That means that water vapor, the gas, will have the higher entropy, because we know that gases generally have higher entropies than solids. And if you remember, you can't always assume this, since I wrote it here that it is a general trend. It does not always hold true. But in most cases it does, so we're just going to assume that it is true. And in this case, the determining factor was the state of matter. Now let's compare a scoop of ice cream versus 2 scoops of the same ice cream. Everything kept constant except for quantity. So quantity will be our determining factor. And guess what? The more stuff, the higher the entropy. So guess what? 2 scoops of ice cream will have the higher entropy of the two. Let's go on to the next question. 2 moles of helium and 1 mole of argon at the same conditions. everything kept constant except for two things, the molar mass and the amount of substance. But what did I say about molar mass? We use that as our last resort. So we want to focus on the amount of substance first, actually. In this case, we can assign values, if you remember. So 2 moles of helium, and if 1 mole of helium is 100, then 2 moles of helium is 200, and this is 100. So which one would have the higher entropy in this case? Well, according to our numbering system and the fact that we are focusing on the amount of substance, means that helium will have the higher entropy, and the determining factor would be the amount of substance. So in this case, we didn't even need these numbers, honestly, because they're the same state. We just had to focus on which one had the more stuff. So last but not least, let's look at this one. Now this one takes some creative thinking. 1 mole of hydrogen gas under 5 atmospheres and 1 mole of hydrogen gas under 20 atmospheres of pressure. Everything kept constant. The determining factor is pressure. Now you might be thinking, wait a second, we didn't learn about this. But we can use something called common sense to figure this out. If you have some helium gas that's under 5 atmospheres of pressure, it's not under that much pressure, so it can move around pretty freely. Now, if we have a helium sample that is under lots and lots and lots of pressure, well, guess what? The molecules will have less freedom. Less freedom means less randomness, and that results in a lower entropy. So guess what? In this case, the 1 mole of hydrogen gas under 5 atmospheres will have the higher entropy because it is more, it has more freedom and thus is able to create more microstates. Now, let's continue on and talk about a new concept. Not really new, just an extension. Let's talk about delta S, the change in S, the change in entropy. Delta S is the final entropy minus the initial entropy. And in this case, it almost always has to do with reactions, as we've seen with delta H. And yeah, a positive delta S means that the final entropy is greater than the initial entropy. So obviously, if this is greater than this, and when you subtract them, you will get a positive delta S. And thus, if there is a positive delta S, there is actually a net increase in randomness. Now, a negative delta S is the opposite. It means that there is a net decrease in randomness. Now, when delta S is 0, there is no net change in entropy, so we can say that the amount of randomness, quote-unquote, stays the same. Let's do some practice. Determine whether delta S is positive or negative or 0 in the following. So the first one, it looks like the reaction is a physical change, and this change is converting the liquid water to gaseous water. And that would be a process called, you could call it evaporation, but it's usually called vaporization. So in vaporization, the liquid turns into a gas. Now this is where the numbering system comes handy. We said before that we can assign values to our substances based on their state. So before I continue, let's just say that this is for 1 mole, and all of these are for 1 mole of substance. So obviously the more moles, the higher the number is. So if you have 2 moles, you'll get 200, for example. So let's apply that logic to this question. So we know that water is 100, and, water vapor is 100, and liquid water is 10. Now, obviously, the delta S, based on this numbering system, will just be final entropy minus initial entropy. 100 minus 10 is 90. 90 is a positive number, so our delta S will be positive in this case. So we can put a fat plus sign there. Now the second question is the detonation of trinitrotoluene, or TNT. Now if you played Minecraft before, you know that TNT is going to explode. And it's going to create a lot of gas. It's actually going to create a gas cloud. And guess what? It's starting from a solid. Let's draw the TNT block here, and it's going into a cloud of gas. Now, if you think about this, you don't even have to assign numbers, although you can. Let's just call this 100 and this 10. Same deal as before. Well, actually, no. This is 1, not 10, because it's a solid. 100 minus 1 is 99. That's positive. This delta S is positive in this case, so we can put a positive sign there. And you don't even need to use this numbering system, because remember, a positive delta S means that there's a net increase in randomness or chaos or whatever you want to call it. So if you blow up TNT, there's going to be more chaos, obviously. So the delta S should be positive. And that's one way to think about it. Now this last one, the dimerization of nitrogen dioxide. 2NO2 is transformed into N2O4 in this dimerization process. And dimerization is simply when two things come together to form one. So 2NO2 became 1N2O4. Now, we can easily assign the numbering system. So, number this as 100, and this is 100, but there are 2 moles of it. So, 200. Let's find the delta S now. So, 100 minus 200 is negative 100. Guess what? This process will actually have a negative delta S. So we can put that negative sign there to satisfy the question. And if you think about this, more moles of gas are turning into less moles of gas. More substance is becoming less substance. So more chaos is becoming less chaos. So more entropy is becoming less entropy, and the change in entropy is negative. So 2 ways to deal with the problem, either through numbers or through talking it through. Now, let's talk about the third law of thermodynamics. We've talked about the first law of thermodynamics in Unit 6 about entropy, so it would be appropriate to finish that off by talking about the third law first. The third law states that a completely ordered pure crystalline solid, so a crystal, has an entropy of 0 at 0 Kelvin. So there's absolutely no randomness for this perfectly ordered crystalline solid. It's going to have literally one microstate because it can't really move around. It has only one possible way of being itself. Therefore, anything else, literally, that's not completely ordered like the crystalline, or not at absolute 0, like that crystalline solid that we theoretically made up, will have a positive entropy. Since S equals 0, it's defined for something that is completely non-random. So in this case, this pure crystalline solid is completely non-random. So anything else will literally have entropy. So here's a little problem that scientists face. It's impossible to get a crystalline solid to absolute 0, actually. We can come close though, but close is sometimes not enough, and sometimes it's ineffective. So instead, we can measure the delta S of other substances, and we're not going to be comparing the delta S of these substances to a crystal at 0 Kelvin, since it is pretty hard to do. We need a better thing to compare to. Now you might be wondering, why can't we compare it to a crystalline solid at 0 Kelvin? Well, it's like trying to visualize $1 or trying to measure the value of $1 by comparing it to $100 trillion, which, like 0 Kelvin, is impossible to get for most of us. We need a better standard, like making the standard of comparison $10 instead of $1 billion, or, and the problem, $100 trillion. So we need a better comparison in order to be able to visualize it more easily. So instead, we can use a comparison such as that the delta S, or just the S naught of the hydrogen ion, and this is aqueous, is 0. So if we set this as our standard, that the standard entropy of the hydrogen ion, and we make that 0, this is a good standard, because this is a standard scientists can use to calculate the standard entropy of other substances, since we can visualize the entropy of the hydrogen ion, unlike a crystal at absolute zero. And notice that this is the not symbol, and that just states that we're at standard state conditions. And we'll talk about that in a little bit. So if you haven't noticed already, you should notice that unlike H, we can actually quantify S because we have a standard for comparison. We said that the S of the hydrogen ion in water is 0. So we have a way to quantify it. Now, using the standard, we can actually have negative entropy values. And that's a little bit weird because didn't we just state that entropy is randomness? How can we have negative randomness? Well, to tell you the truth, in reality, we actually have positive entropy, since of course, as long as there is some randomness or entropy, then it will have a positive entropy. But when we compare it to H+, dissolved in water, it is actually lower in entropy when compared to this. And remember, this is 0, and if it's lower than 0, it's going to be negative. So they have a quote-unquote negative entropy. It has a positive entropy, but when compared to H+, which we usually always do, it will actually have a negative entropy. For example, the hydroxide ion, I'm assuming dissolved in water, has a standard molar entropy of negative 10.75 joules per Kelvin per mole. Now, these are the units, and let's get into the units. Entropy is simply energy per Kelvin, J/K, for any amount of substance. So note that it's for any amount of substance. Now, molar entropy is a little bit more specific, obviously. It's actually the entropy of 1 mole of substance. So we have a J/K, but we also have to divide it by 1 mole to get the fact that it's the amount of entropy per 1 mole. So it would be, I guess you could, yeah, we could do this. So this is the units for entropy, and it's per mole. And if you simplify this, you actually just get that. You just put the moles, and you multiply it by the K on the denominator. Now, a standard molar entropy, notice how there's an extra word there, is the entropy of 1 mole of substance at standard state conditions. That's what it means to be standard. And if you remember, it's 1 atm, 1 molar, and typically 25 degrees Celsius, which is the temperature that scientists have easy access to. Now, we actually have a standard molar entropy table that gives us the values for elements and substances, which is cool. So note, unlike the heat of formation, the standard entropy for elements is not equal to 0. So, for example, we know from chapters or unit 6 that the change in the heat of formation or the enthalpy of formation, whatever you want to call it, is 0 kilojoules per mole, because that's the definition of the heat of formation, and it states that all elements in their natural state will have a delta HF of 0. But that's not true for delta, or just S in this case. For S naught, the entropy of substances is actually not equal to 0. So for a natural element like O2 gas, while the delta HF is going to be 0 because that's a rule that we follow, the entropy of that substance is actually going to be a number that's not 0. In this case, the standard entropy for oxygen is actually 205 joules per Kelvin times mole. Now, let's do one last thing. Let's go back to Hess's law and apply it to this chapter. When given the delta S of a series of reactions, the delta S of the overall reaction is actually the sum of the individual delta S's of the reactions. So if you don't know what Hess's law is, well, you can review that. And let's take a look at why this works. Now, the reason why we could use Hess's law for delta H's or enthalpies is because H is a state function. And guess what? S is also a state function, meaning that the entropy of the substance, no matter what path it takes, will always be constant. Therefore, the delta S only depends on the products and reactants and not on the path the reactants took to get to the products. So now let's do a practice problem based on everything that we've learned. So this practice problem will involve us finding the delta S naught of the combustion of methanol, which is CH3OH. So this reaction is a combustion reaction. And we are given the S naught for each of the substances that are involved in the reaction. And we are going to find the delta S naught by using this cool rule over here, that the delta S naught is actually equal to the total entropies of the final, or the products, minus the total entropies of the initial, or the reactants in this case, because final is after and initial is before. So we have to find the total entropies. So how do we do that? Well, let's start off by finding the total amount of entropy for these 2 moles of carbon dioxide gas. According to this, the molar entropy of carbon dioxide is this. If we have 2 moles of it, we're going to multiply it by 2, since this number only gives us it for 1 mole, but we need 2 moles since there's 2 of them here. So let's go ahead and do that. So 2 times 213.8. Now we have to add that to the total amount of entropy in 4 moles of water vapor. And the question tells us that 1 mole of water vapor is 188.8 joules. So let's go right ahead and do that. So 4 times 188.8. Now I actually want to include units so you guys can see what's going on. And this would be 2 moles to 4 moles, and this would be joules per Kelvin times mole. And now we have to actually subtract. And what would we be subtracting? Well, the total amount of entropy of the reactants. So let's put a big parentheses around that. We start off with 2 moles of the methanol, and we know that the molar enthalpy of methanol is 237.6 joules per mole times K. Now we have to actually add this to the other component of the initial, the initial entropy. Those words are kind of confusing, honestly, but we will get the hang of differentiating between the two. So 3 moles of O2, and let's see, the molar entropy is going to be 205.0 joules per mole times K. Now we have to put all of that in parentheses because all of this stuff is actually the S naught initial, and all of this stuff right here, we can even put these in parentheses if we wanted to, is the S naught final. And notice how we're just subtracting it right in accordance with the equation we have, which at this point is covered with marker. So I'm going to tell you why this works. So notice how the moles cancel out, and you end up with an entropy value of 2 times 213.8 joules per Kelvin. So if we do the math, 2 times 213.8 is going to be 427.6 joules per Kelvin plus, let's see, 4 times 188.8 to get 755.2 joules per Kelvin. And we're going to actually subtract that by 2 times 237.6 for 75.2 joules per mole Kelvin plus 3 times 205.0 So I'm actually not going to write 3. I'm just going to write the answer, 615.0 joules per Kelvin. Notice how the moles cancel out, leaving us with entropy values. So doing the math, 427.6 plus 755.2 minus parentheses 475.2 plus 615 will give us, well, the delta S of the reaction. So that is actually equal to 92.6 joules per Kelvin. And notice how it was per reaction. And as we know so far, if it's per reaction, it's per mole of reaction. And this we learned in Unit 6 when we dealt with the delta H and the units for it. And the units for delta H is kilojoules per mole of reaction. So in this case, same idea. It would just be joules per K times mole of reaction. Or you could just put mole, but that mole of reaction really makes it clear that we are dealing with 1 mole or just 1 reaction. So that's the answer, and voila! We found the delta S naught for this reaction by taking the individual S naughts and adding them together and subtracting them from the initial. And remember to always include coefficients, and remember it's final minus initial. So before we end this video, we need to talk about one last thing. And in this case, we're actually going to switch to a new screen. We're going to talk about the last law of thermodynamics. Well, technically not the last, but the last that we'll cover in chemistry in the case of these videos. And it's called the second law of thermodynamics. It states that in any spontaneous process, there is a net increase in entropy when considering both the system and surroundings. In other words, the universe likes to make things more chaotic, more entropy, or random over time. So we actually have a formula for this. The delta S of the universe is just the delta S of the system and the surroundings. And it has to be a net increase. So the universe has to have a net increase in entropy. That means that delta S has to be positive. And guess what? It's positive when it's greater than 0. And oops, I shouldn't be putting that greater than or equal to, because it's just greater than. So as long as this or this is greater than 0, we're good. So let's talk about more things. Just like that, we went over all 3 laws of thermodynamics. Yay. And of course, the first law is in the unit about enthalpy, which talked about work and heat. So now let's do some problem solving. If I give you the reaction, the delta S of a reaction, and I tell you that the delta S of a reaction is negative 282.3 joules per mole times Kelvin, or mole of reaction, up to you. Now, I want you to figure out what delta S of surroundings is needed to ensure that this reaction is spontaneous. So we have to do some logic building. So we remember that a spontaneous reaction occurs when the delta S of the universe, or the net change in entropy in the universe, is greater than 0. And we established that all the change that's going on in the universe consists of the system and the surroundings. So this dot might be the system, and everything else around it is the surrounding. And guess what? Everything else around it plus that thing is equal to basically everything, or the universe. So we substitute the delta S of the universe for the delta S of system and delta S of surroundings. And of course, they have to be greater than 0. So we know that the system, in this case, that we're focusing on is actually the reaction. So in this case, we pretend that this is, I don't know, a cup, and a reaction is going on in there. This reaction that's going on is actually the system. So the system is the reaction. Therefore, the delta S of the reaction, as I gave you at the beginning, is actually equal to the delta S of system. And from this point, it should just be all algebra. So I substitute this negative 282.3 into the delta S of the system, add it to delta S surroundings, it has to be greater than 0, and adding to 82.3 both sides, we get that the delta S of surroundings needs to be greater than 282.3 joules per mole times Kelvin. Now, let's actually prep for video 11.3, where we will discuss delta G, or the change in Gibbs free energy. But for now, let's not focus on that, and let's focus on this. So a cool thing is that the delta S of surroundings, or the change in chaos or randomness of the surroundings, is actually just equal to the heat of the surroundings divided by the temperature, of course in kelvins, because in chemistry, when you have temperature, you usually want to plug in kelvins if you can. And this is actually equal to the negative Q of system over T. Now, why is this? Well, if you remember from Unit 6 with the calorimeter, we know that the heat that is absorbed by the surroundings, such as when, I don't know, let's just say we're cooking marshmallows and there's fire. This fire is the reaction and it's heating up the surroundings, so the surroundings will gain heat. Well, that's actually equal to negative Q of the system. In this case, well, actually, this is a terrible example. Let me redo my example and give you a better example. Let's take a cup of water. This cup of water, let's just say it's super hot and it's giving off heat to the surroundings. So the surroundings will, of course, gain heat. So this Q of surroundings represents the surrounding air gaining heat. Now, this is actually equal to the amount of heat lost by the system or the water. So the water is losing heat, and the amount of heat that it loses is actually equal to the amount of heat that's gained by the surroundings, because nothing is created nor destroyed, it's just being transferred. So this equation is valid. Now, all we did was we substituted this for this, and we can actually go on to say that the more heat a reaction releases, the more the Q surrounding is, because, if there's more heat that's being absorbed by the surroundings, the larger QSURR is. Now, we have to remember that delta H is Q, but for 1 mole of substance, usually. So we can substitute, the Q of system for literally the delta H of the reaction. And we get this cool equation right here, super duper useful. The change in entropy for the surroundings is actually equal to the negative delta H of the reaction divided by T. Now, does this make sense? Well, sure it does. For an exothermic reaction where delta H is negative, then we will get a positive delta S of surroundings, because obviously negative times the negative delta H divided by a positive T will give us a positive number. So in this case, if the delta H of reaction is negative, the delta S of surroundings is positive. And this makes sense, because in an exothermic reaction, if you think about it, now we can use the fire analogy with the marshmallow. If this reaction is releasing heat, and it's thus exothermic, don't you agree that the surroundings will have a positive entropy? Or in other words, won't this marshmallow heat up in temperature? Won't the air be heated up? Well, yeah. So this claim that an exothermic reaction will have a positive delta S of surroundings makes a lot of sense, actually. So if heat is released, then the surrounding will heat up and increase in entropy, just like I said with the marshmallow and the air. So we conclude that a negative delta H reaction will lead to a positive delta S of surroundings. And the opposite, or the converse, is true as well. If you have a positive delta H reaction, there's going to be a negative delta S of surroundings. Now, that's actually all for this video. Thanks for watching, and have a wonderful day, everybody. Hope you learned a lot.